Welcome back to ECE 442-542. Homework number 3 is available. Not that you have everything you need to know to work through that, but it's not due until the 27th of February, so you have a few days to work on that. Hopefully after today's class you'll be able to work more of the homework problems on that assignment. Exam 2, just as a reminder, is a month after Exam 1. It's the 8th of March. Solutions to exam number 1, I think, should be posted now. They better be available on D2L. And I also posted a resource for the region of convergence in unit number 3 on D2L, and it's at the top ahead of all the lecture material if you want a little bit more information about the region of convergence. Today what I want to do is talk about inverse C transforms, and we'll start with trying to connect that with where you've already been, inverse Laplace transforms. Hopefully we can remember how to do those, and we'll talk more about the region of convergence in terms of the patterns with respect to poles, and how do we determine from the region of convergence pattern whether we have a causal sequence, an anti-causal sequence, or a two-sided sequence. And that is not necessarily the same. It isn't the same as whether your response is bounded or unbounded. And so I'm using this unbounded many different ways. If I say the region of convergence is unbounded, that's not the same as your time response being unbounded. You could have a bounded time response and have an unbounded region of convergence. Those are consistent, but depending on your location of the poles and the region of convergence. Hopefully that will allow us to better understand why we are interested in poles inside the unit circle to determine stability, and that's typically because we are dealing with a system that's causal. If we kick it, then it moves. It's not moving before we excite it. We have to excite it before it starts moving. That's a causal system. In this class, it's a controls class, and that's typically what we're playing with. But then that allows us to think about poles inside the unit circle giving us a stable or a bounded response. We can, if we have an anti-causal sequence, we can have poles outside the unit circle that give us a bounded response. That's okay. And those maybe seem counter to each other, but just remember, one is dealing with a causal time domain waveform and the other one is an anti-causal. Then we will get into a new topic, which is discrete equivalence, and that's how do we go from a analog system, whether that's a system or maybe it's a filter, how do we translate that into something that we could now put onto a digital device or a computer? How do we make a discrete time system out of that, or find the transfer function for a discrete time system? Let's start today with the following. Suppose that, and this is trying to get us connected with where you've already been. So let's do an inverse Laplace transform. And suppose that I give you capital X of S is 6 over S plus 2, S plus 3. And I want you in a minute to find what little x of t is. So you have a minute to find little x of t from capital X of S being 6 over the denominator of two-factored terms. That's giving you more information, so you shouldn't have too much time to inverse Laplace transform that, or needed to inverse Laplace transform that. And I guess you can work it work your neighbors if you want. Oh, you don't need my permission. Okay. This isn't an exam, so that's okay. You can talk with a neighbor to figure out what is little x of t if this is capital X of s. And our minute is up, isn't it? How did you approach this problem? Or what did you immediately see a structure of the time domain response given this capital X of s? And I would like for your heads to all be going up and down in a yes pattern, not in a no pattern. What's the structure of the solution for x of t? Is that the structure? Now, how do you find c and d? Partial fraction expansion. Did anyone do the partial fraction expansion? You act like we don't believe you. There's doubt in the room. I see. No, what is c? How do we do the partial fraction expansion? You can do it on your calculator, can't you? Some of you have a calculator, and what's the command? Well, we'll get to that. But here you can multiply through by the factor underneath c, which is s plus 2, giving you, and then you evaluate at the value of s that causes that to vanish, and in this case, we have 6 over 1, or 6. So in our case, c is 6, and d, we multiply through by the factor underneath d, which is s plus 3, evaluate at the value of s that causes that factor to vanish, and now we have minus 1 divided into 6, or minus 6. So that x of t is now this 6e to the minus 2t minus 6e to the minus 3t for t greater than or equal to 0. I was actually encouraged that no one pulled out their calculator, but if you did have a higher level TI, a TI Inspire or a TI 89, you could actually just issue the expand command, and that will give it to you. You can just say, and sometimes depending on your calculator, it's easier to put it in terms of x, but you might say x plus 2 times x plus 3, close up all of the right parentheses, and it should give you the answer of 6 over s plus 2 minus 6 over s plus 3. And the idea is you can now immediately inverse Laplace transform that partial fraction expression. Yes? So now the t greater than or equal to 0, the question was, is that the same as multiplying everything by the unit step? How many think that's, did you understand the question? The question, I think, was as follows. X of t is equal to 6e to the minus 2t minus 6e to the minus 3t u of t. Is that what the question was? Is little x of t the same when I multiply everything by the unit step versus saying t greater than or equal to 0? Is that equivalent? Or are you going to ask another question? What do we think on this question? Is it the same? How many So let's do thumbs up, thumbs down. Thumbs up is yes, thumbs down is no. On the count of 3. 1, 2, 3. If you had me for 320, I want to see all your thumbs in the right direction. U of t is, in this case, just acting like a switch. And we're not trying to get a ride home with our thumb. Okay, but you should have had a thumbs up. It's yes, these two are equivalent. U of t, the unit step, is really just acting like a switch. It's turning that expression on. Just think what U of t does. When the argument of t is non-negative, U of t is 1. And when t is negative, it's 0. So you have the same expression for those two, or I'm sorry, those two expressions are equivalent. Now, I had a different question, I thought, that was wanting to be asked. Do you still want to ask that question? Okay. So I'm just making sure everyone is awake. The question was a correction question to my mistake. It should have been 6 over the quantity. Yes. In order to have the denominator or the answer giving us 6's in the numerator. So yes, I obviously wasn't writing down my notes properly, and I got carried away and quickly was just writing down the denominator and messed up. So maybe I got 2 points out of 100 on that problem. That's okay. I'll make up for it on the others. It's better than 0, right? Any other questions? With that background, that's now connecting us to where we have been. Now we're ready to move forward. Let's do an inverse Z transform. And in this case, let's find little f of n. If capital F of z, let me see if I can get the right expression, is z over z minus 1/2, z minus 3/4 for the absolute value of z greater than 3/4, where this is the region of convergence. What's the thought process that you maybe are already working through mentally in terms of this particular problem? What can you start to do to find little f of n? Or what is the answer in the back of the book that you're trying to come up with? Do you already anticipate a structure for this? A structure for the solution? Can you anticipate what that is based on this expression for capital F of z? You guessed the you didn't guess, let's say you knew the structure here for little x of t based on the denominator factors in capital X of s. Can you do something similar for little f of n? Can you find the poles of capital F of z? Those are the values of z that cause the denominator to vanish. One of those poles is at 1/2 or 0.5, depending on how you're processing that. So here you might say alpha 1, 1/2 to the n. And that's really a decaying exponential response. Well, I'm going too far. We know this structure so far. It's 1/2, and what's the other piece? 3/4 to the n. Now, Do you know what indices this is valid for? What is little n? Is it two-sided? Is it left-sided? Is it right-sided? Is it anti-causal? Is it causal? Which n range, or what range of values for n are allowed given this information for capital F of z? Or can we determine that? What's the region of convergence telling us? Here we know that in this z-plane sketch, we actually have poles at 1/2 and 3/4, and our region of convergence is beyond or exterior to all of our poles. Does that remind you or clue you in on where the values of n need to be defined, or where little f of n is valid? It's the region of convergence goes off to infinity, does it not? And I might say the region of convergence is unbounded. Does that tell you something about, if you thought about the expansion of your z transform and you allowed that z transform to be evaluated for a value of z in the region of convergence, that z could go off to infinity? Which values of n does that basically say cancels or does not allow any of your time sequences to be anything other than 0? Maybe I didn't say that very clearly. Yes, so now I'm looking for which sided it is. Is it right-sided? Is it causal? Or is it left-sided? Is it anti-causal? I'm hearing this. It is right-sided. So now we know, and now, can you tell me anything about the bounded nature of the response based on what I have on the page? And you could answer this question using a couple of different pieces of information on the screen. Now I'm asking, is this little f of n bounded for all n? Is it always below some finite number in value? Is little f of n bounded? Or does it go off to infinity in magnitude? For these values of n, little n, non-negative. You should be able to look at the right-hand side of little f of n and answer that question. Now you have 1/2 to higher and higher positive values, 1/2, 1/2 squared, 1/2 cubed, or 3/4 squared, cubed. That's something less than 1 that's getting raised to higher and higher power. That's collapsing. That's vanishing. Its biggest value occurs when little n is equal to 0, and then it just keeps going down from there. Does everyone see that? That's one way to answer that question. Is it bounded? And the answer is yes. So now we have a bounded f of n because we have a what? We have an unbounded region of convergence. Yes? Our region of convergence is unbounded. It's going off to infinity. Another way to answer this question, as far as is your response, time domain response, bounded, is to look at where the unit circle is relative to the region of convergence. The unit circle is this nice circular region that I've now indicated by the dashed line. And if that unit circle is inside or contained in the region of convergence, you know that your time domain waveform is bounded. That's the second way that you could have answered this question. So if the region of convergence contains the unit circle, which this one it does, then you know your time domain waveform is bounded. Yes? So now the question was, in f of z, does it need to have a numerator that's z squared? Is that what the question was? And maybe you're getting ahead of me. We really haven't solved this yet, have we? Can you now solve for little f of n? We just are guessing at the answer in the back of the book, or we're trying to give ourselves some comfort as we approach the solution to this problem. And the comfort is we've now anticipated what the answer is. It has this structure. We know it's well behaved. If somebody starts asking you, you could start writing all of this down on a napkin to give yourself more time to think. If this was an interview question and somebody said, oh, here's capital F of Z, can you tell me about it? And you could say, it's blue. But then you could just give yourself time, and then you could say, I have a pole at 1/2, and I have a pole at 3/4. That tells me the structure of my time domain response. And then you could go, oh shoot, what's region of convergence? How does that relate? And you could start sketching this. You could say, oh, I could look at the z-plane and sketch the region of convergence. And then that might start triggering, and you can say, oh, the definition of the z-transform, and you can start to see what values of n are going to allow for little f of n to be non-zero, or you have now a right-sided sequence. Where was I going besides an interview question? Oh, how do we now find little f of n given capital F of z? Yes? Did anyone hear that? No? Do I have to repeat it? Because I didn't hear it very well either. But what we want to do is we want to end up with, I think the comment was, we want to end up with something that we can find in the Laplace, in the Z-transform table that we could then take into the time domain. Here, that was, I hope, clear. C over S plus 2. Oh, we know where that is in the Laplace transform table. If we had a Z-transform table, we just happen to have available to us, which of these are we looking at? Maybe I should label these. Here's, let's say, row 1, row 2, row 3, row 4, row 5. Which of these lines do we want to use or think we want to have for our pair to go back into the time domain? And now I've just given you 5 lines so that we can answer on our hand. I could give you more. I guess we have 10 digits, but I can't even see 5. So let's just go with 5, and you can answer with 1 finger, the index finger, 2 fingers, 3 fingers, etc., or a full palm, and you can put that up against your chest when I say 3. Okay, 1, 2, 3. Yeah, we have a few signs going, signaling going on here. I would like to see number 2 being a very peaceful feeling coming across the class. We're looking for terms that look like z over z minus, let's say, r. That's what we would like to find. And what's going to happen if we invert, or if we partial fraction expand z over z minus 1/2 z minus 3/4? Will we end up with this term z over z minus r? If you partial fraction this guy directly, what will you obtain? Do you see that you would get an a over z minus 1/2 plus a b over z minus 3/4? If you can, z is a complex number. You can do just like what you did with s. You multiply through by the factor in question and evaluate it at the value of z that causes that factor to vanish. But these, a over, does not have a z in the numerator, does it? And if we just quickly did a partial fraction expansion, we're going to end up with this right-hand side, which doesn't match up with a transform pair in our table. We want to end up with a z sitting up on top, and the way to do that is to essentially, what? What if we put that z in the denominator of f of z? So now we just divide both sides by z, and we now on the right-hand side have that. Now we can partial fraction 1 over z minus 1/2 z minus 3/4 to find the unknown coefficients, let's say a bar and b bar, and once we have a bar and b bar, then we can multiply both sides through by z again, and we'll have the structure that we want. So the question was, why is this first expression problematic? What I'm suggesting is we're missing a z. And I want a z up here so that I have a z in my numerator. And then if I have this, I know that I have alpha r to the n. I can immediately use the table pair to go into the time domain. Here I'm missing a z factor in my numerator in that first partial fraction expansion, and I can obtain it from the blue line by now saying, oh, now f of z will actually be a bar z over z minus 1/2 plus b bar z over z minus 3/4, and now I can write down little f of n is a bar 1/2 to the n plus b bar 3/4 over n, and by the region of convergence, I know that's a causal time domain waveform. Like in the Laplace transform, now we need to find a bar and b bar. But that we can do with our calculator, or we can do it with exactly the same technique that we used before, except now we want to use the f of z over z expression. We want to set it up so that we end up with a result that's easy to match up with our z transform pairs in the table. Is that clear? Can we find a bar? You can find a bar, huh? Yeah, I wondered why we were laughing. Yeah, you'll find a bar after class, and I'll find a B after class. No, I'll find B bar. No, never mind. I don't want to find a B after class. All right. So now we need to find a bar, a blue a bar, an a bar in this class, and we can multiply through by z minus 1/2 and evaluate at z equal to 1/2. And now I have 1 over minus 1/4, or minus 4 for a bar. Similarly, I can find b bar, multiply through by the factor that was underneath b bar, which was z minus 3/4, which leaves me now with z minus 1/2, evaluated at 3/4. Or b bar now is 4. And I now know that little f of n is minus 4, 1/2 to the n, plus 4, 3/4 to the n for n greater than or equal to 0. And we know that it's n greater than or equal to 0 because of what piece of information in the problem statement? Why can we say n greater than or equal to 0? That was our region of convergence argument, which, if we now looked at capital F of z in terms of the z transform, whoops, we know by definition that's what capital F of z expands out to if we wrote it in terms of powers of z, or z to the minus 1. And with our region of convergence, and we were told this, that it was beyond 3/4. If I now pick a point out here and let that point get really, really big, what happens when I plug this point into that location in my infinite sum expansion for capital F of z? Now I have z to the minus minus 1, or I have z, and I'm letting z go off to infinity. That tells me that that coefficient has to be 0. That's where the right-sidedness or the causal characteristic of f of n is coming from. We also can see that that has to hold for all of these other coefficients or values of little f of n for negative values of n. They all have to be zeros. Otherwise, they would give an unbounded result for capital F of z, and we know that f of z is well behaved. It has to be bounded. We were told what it was. It was this z over z minus 1/2 times z minus 3/4. And again, you could do this with your calculator. You could issue the expand command. You could say something like 1 over z, and now it is 1 over because I'm trying to expand f of z over z. It's now z minus 1/2 times z minus 3/4, and that should give rise to the answer, which it might spit it out in a different order, but it might do something like that. Oh, and it probably won't give it in the ratio form, will it? Questions on inverse Z transforming. How to connect the expression and the region of convergence to tell you what you need to know about the time domain waveform, let's say little f of n. The structure and the coefficients can all come from capital F of z, but where those little n's are depend on the region of convergence. What if I had a different region of convergence? Maybe my region of convergence is annular or donut-shaped or bagel-shaped. What if I had the following z-plane sketch? Suppose I had a pole at 1/2 and a pole at 3. And, oh, I didn't give myself enough space, but you get the idea. This is supposed to be a circle, and so is this. So I apologize if my donut is a little lopsided, but my region of convergence now is in between these two poles. My region of convergence is now the absolute value of z is less than 3 and bigger than 1/2. What does that give rise to in terms of where my little n's are, or what values or range those are spread out over? Is it right-sided? Is it left-sided? Is it two-sided? Well, let's convince ourselves that it's two-sided via an example. And to make it cleaner, let's go the other direction. Let's do the Z transform, and then we'll know why we ended up with the expression what we did, or an annular region. Suppose that we now say that little f of n is made up of two pieces. One function, f sub 1 of n, let's say is 2 times the quantity 3 raised to the n for n negative. And let's say that f sub 2 of n is 4 1/2 to the n for n non-negative. Or we could have said that f of n now is really f1 of n plus f sub 2 of n, where we have the understanding that f sub 1 of n is only defined for negative n's, and f sub 2 of n is defined for non-negative n's. What's capital F of z? Or what's a property of the Z transform that we can apply that will allow us to express capital F of z in terms of this factored form of little f of n? Now all you have to do is hit the shift key on your typewriter. Capital F of z is capital F sub 1 of z plus capital F sub 2 of z. If we can find those, then we can put them together and have capital F of z. What's capital F sub 1 of z? by definition, and now we have negative values of n, meaning now we can go from minus infinity up to minus 1 of f sub 1 of n z to the minus n. Or that's this sum from n equal minus infinity up to minus 1. F sub 1 of n was 2 times 3 to the n z to the minus n. The 2 doesn't have an n associated with it. We're not raising that to an nth power. Let's just get that out from underneath our summation. We have 2 times the sum from n equal minus infinity up to minus 1. And we could write this as 3 over z, where z to the minus 1 is going to put z downstairs to the n. Or, now I need to sum this, and this looks a little bit different from what I'm used to, so let me just solve it. Suppose I now say, well, let me look at what this does. S, and let me go backwards. Let me go from the top down to minus infinity. S is equal to 3 over z to the minus 1 plus 3 over z to the minus 2 plus 3 over z to the minus 3, etc. Is it clear where that's coming from? And I'll have to scale that by 2 to get my eventual answer. Yes? It depends on where you're sitting in the classroom. That was a skinny 2, so that was a minus 2. The question was, how did I get minus 1 twice? Depending on where you're sitting in the classroom, that may or may not be clear. Who knows what it is if you can't see. So I'll sit up there. Well, the table will fall if I sit on the table. Oh, on the chair. Oh, okay. Yes, I'm not thinking very clearly. It's way past my bedtime. You know that. All right. So is that clear now? What's the common ratio between these terms in the summation? Or what factor is there? 3 over z, right? And I'm just raising it to higher and higher, and I'm actually raising it to more and more negative powers. What do I want that common factor to be now that I'm raising it to negative exponents? This is sort of just the upside down version of what we've talked about before. Typically we said we were raising these terms to higher and higher powers, and so we needed the factor, the common ratio, to be less than 1. Now what do you think we need? Now we need it greater than 1 if we're raising it to powers that are negative. So this is now 1 over 3 over z, etc. So we need this 3 over z magnitude to be bigger than 1 for this to converge. We want those terms to be shrinking as we go further and further into that summation. So for this capital S to be well behaved, means that we need 3 over z to be bigger than 1. We need that to be bigger than 1 because it's really in the denominator. Is that clear? Question? We could play with however you want to play this. But here I was just doing it differently, just so if somebody wants to see it a different way, maybe it speaks to them this way. If it doesn't speak to you this way, you can do it a different way as long as we're consistent. So you can put that negative power inside the parentheses, invert things, and make it look more consistent with what you're doing. Here I'm doing it different just to do it different. Now, if I want to find out what capital S is, what could I multiply that same expression by to sort of give me the same looking tail? If I want my tail to look the same, if I now have S, but I don't want it to be the same. I don't want to end up with 0 equals 0 when I compare those. But is it clear that if I multiplied both sides by 3 over z, I would start to get something that looks the same in the tail, but I would introduce a 1 in the front, meaning if I multiply 3 over z to the minus 1 by 3 over z, I end up with 1, and now the tail looks exactly the same. Not my tail anymore. I can't say anything in this class, so you're just going to have to watch the lecture and be entertained by the lines appearing on the screen. Tough audience. But now do you see what I'm trying to obtain? If I now compare or subtract the bottom from the top, I end up with 1 minus 3 over z to the s is equal to minus 1. Or now s is equal to minus 1 over 1 minus 3 over z. And if I multiply by 1, a nice one, which is z over z, I end up with minus z over z minus 3. And where did I want that z to be defined? For what values of z is this expression well behaved? Or is the transform bounded? Bounded when 3 over z was bigger than 1, or this now says that I need, if I multiply through by z, I need the absolute value of z less than 3. It's now inside a disk bounded on the perimeter by 3. So that to picture, for f sub 1 of z now has that for my region of convergence, and where is my pole? My pole can't be contained within the region of convergence. It's on the boundary, and for what values of little n is this going to be valid? Well, that was stated in the problem, wasn't it? But you could look at the expression and verify that when we have the region of convergence interior to our poles, then we have a left-sided or an anti-causal sequence. Question? What happened to the 2? The 2 has not yet been in there. F sub 1 of z needs to be 2 times s, doesn't it? So now this needs to be minus 2, whatever we ended up with, z over z minus 3. There's the 2. Is that okay? So if we need capital F sub 1 of z, it keeps that 2. We just were looking at the piece that didn't have that 2 in it, but now we're bringing it back. Is that okay? Yes. Does the 2 change the region of convergence? What do you think? Anyone want to answer that? What piece were we looking at when we determined the region of convergence? It's a good question. Do we now have to go back and rethink our region of convergence? If we have a number that's bounded, what happens to that behavior of a bounded value if we scale it by 2? Does it stay bounded? It gets bigger, but it's bounded. So that 2 doesn't impact our region of convergence. That infinite sum is what was determining the values of z where that was valid, and we just want it to be bounded, and bounded is bounded. Does that help? Questions on that? So now we have a region of convergence interior to one of our poles, but we still have a second piece to this z transform. We still have capital F sub 2 of z, which was 4, I hope, 4 times this sum from n equals 0 to infinity of 1/2 to the n, z to the minus n, and this piece now is this 1 over 2z, and what do we want raised to the n? And what am I doing that for? I'm trying to find the common ratio between my terms in this infinite series expansion to produce, what do I need my common ratio to be in terms of its behavior to have this infinite sum well behaved? Now I am raising it to higher and higher powers of n. N is going from 0, 1, 2. I need this common ratio to be, if I'm raising it to higher and higher powers, I need it to be less than 1. And this now gives me a region of convergence. If I multiply through by the absolute value of z, I now have z to be bigger than 1/2. It's now beyond that pole at 1/2. And what is this going to end up being in terms of an expression? We won't go through the s's. It's now 1 over 1 minus the common ratio, which if we clean things up, it will be times z over z minus 1/2. And that's true as long as the absolute value of z is larger than 1/2, or now we have in the z-plane, we have a pole at 1/2, and our region of convergence for f sub 2 of z is now beyond 1/2. And we need actually this region of convergence to be simultaneously consistent with the region of convergence for our first piece, which was f sub 1 of z. We need to take the intersection of those two regions of convergence and hope they have some overlap. In this case, now to find the region of convergence for our overall waveform, we now need to take the region of convergence number 1 and intersect that with the region of convergence for the second expression. Doing that now allows us to see that, oh, indeed, we are going to end up with this donut-shaped region of convergence. We have a region of convergence beyond 1/2 and interior to 3. And if I wanted to get creative, maybe I should have colored all of that in different colors, and you could have seen where they overlapped, but I'm not that creative. Yes? So now the question was, is it really going to matter? And my answer is it's probably not, because we're really looking at the extremes. In terms of the scaling issue, we would be looking at scaling that when it gets really, really small, and that's near the origin. That's actually gone away now with this intersection. And if we scaled the region beyond 1/2, it's getting big, 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 big. But if we have a finite pole that's bounding it, it's not going to really matter. We're now bounded by our poles. Because what did we learn last time about the region of convergence and poles? We cannot have any poles in our region of convergence, right? The poles are always outside. And what do we also know about the region of convergence and ants? A-N-T-S. The ants have to be able to crawl around and get to any point in the region of convergence. We can't have disconnected regions of convergence. Now, in this particular example, is little f sub n bounded? Was that what I called it? So I started with capital F of z, which was here. And now I want to know, is little f of n bounded? Now I have a 3 raised to higher and higher values of n. But what are those n's? They're negative, aren't they? So they're putting those in the denominator. So now I have 2 times 1 over 3 to the 3 squared, 3 cubed. That's well behaved. And for the other piece, the little f sub 2, I have 1/2 squared, 1/2. That's less than 1. That's shrinking. From that, we could argue that it's bounded. Maybe it's not as clear, but what's the other strategy that we said we could put at our disposal or have at our disposal to assert whether this is a bounded time response or not? So now we need to look at the unit circle and see if it lies inside the region of convergence. And here is our unit circle. Obviously, I haven't drawn this very accurately. But now I hope it's clear that this unit circle is inside our region of convergence. So another way of concluding is little f of n bounded, yes, and f of n was both right-sided and left-sided. It was two-sided. It was designed, or it was defined for all values of n. The side that was right-sided decayed. The side that was left-sided decayed as we went further and further away from n equals 0. Now that we're having so much fun with rocks, with regions of convergence, let's look at another one. Suppose that I now have the following region of convergence. And maybe so now my region of convergence is beyond something. Let's put a pole at 3 and another pole at 1/2. So those singularities are the same as before. And now I have the absolute value of z bigger than 3. I have an unbounded region of convergence. What do I know about my... So this is another region of convergence. With the same poles. What's the structure of this answer? If that was capital W of Z, what's little w of n in time? Can you tell me what the structure is based on the picture that I've sketched? This is now the z-plane. And I have two real poles. Can you tell me anything about the structure of little w of n? Are we clear with that structurally? Now, what ends is this defined for? Can you tell that from the region of convergence? And now one way might be to say, okay, where is my, if I'm staring at this, which hand lies inside the region of convergence? And it's the right hand. Is this a left-sided or a right-sided sequence? It's a right-sided, it's causal, isn't it? So this is now true for n greater than or equal to 0. Is this sequence bounded? And you can see that two different ways, I hope. One, by just this structure. This one is no. W of n goes unbounded as n marches off to infinity. But what about the other strategy that we've talked about today? If I show you the region of convergence, or the z-plane, what are you looking at now? If this is the unit circle, is that, and here the wording, it's maybe not very easy to state, but is that on the region of convergence, that unit circle? Does it lie on top of? Does the unit circle lie on top of the region of convergence? No. So that also says the unit circle is not contained within the region of convergence, which now says that we have an unbounded time domain waveform. The region of convergence does not contain the unit circle. So let's look at some observations. Relative to the region of convergence. And maybe I should try to sketch this a little bit better. Let me try to sketch a generic annular region. And let me put some poles here. Let's say I have a pole at 1 and a pole at 2. I'm sorry, I'm labeling those 1 and 2. Those aren't necessarily at location 1 and 2. And let's say this pole is labeled 3 and this pole is labeled 4. This is the z-plane. There's the real Z and the imaginary Z. And, oh, and I didn't sketch the region of convergence. Let's make it annular. Meaning I don't just have to have two poles. I could have many different poles, and they may be in various locations, but two of those poles, if I have an annular region, will be bounding my region of convergence. In this case, number 3 pole is just inside the region of convergence, and the number 1 pole is just outside the region of convergence. Is that clear? Maybe not from my sketch, but that's what I'm trying to imply. What we want to do now is make the following observation. We want to be able to associate, and this should be clear from the previous example, associate the poles larger than, I never know how to word this to make it clear. Now I'm talking about the poles. So now the poles that are beyond the region of convergence, or beyond the annular region, and which poles are those? And that will maybe determine whether my wording is clear or not. Now I want to associate the poles that are larger than the annular region or lie beyond the annular region. Which poles? 1 and 2 or 3 and 4? 1 and 2. That's what I'm meaning by beyond or larger than. What time range do we associate with those poles? If our poles are beyond, then these are what the region of convergence is interior to the poles, and that was, now if we looked at that, we would say, oh, my left hand is in the region of convergence. This is a left-sided or within less than 0. Or we might say that the region of convergence is interior to poles 1 and 2. And the other half, and the poles, let's say smaller than, or interior to. I never know what is going to be clearer, since I'm using interior in two different ways and two different, in the same, now I'm confusing myself. So let's say, and the poles smaller than the annular region, or interior to the annular region. Which poles are those? Which poles are interior to the annular region? 3 and 4. So those poles we need to associate. Now, if we looked at those poles and just concentrated on those and put our hand, a particular hand, inside the region of convergence, which hand would be inside the region of convergence associated with poles 3 and 4? And I apologize for those of you that are watching at home, but you can now go up to the board or to your screen, expand it as big as you want, and put your hand, hopefully it was your right hand. This is now going to then correspond with n greater than or equal to 0. Or that's with the region of convergence when it is exterior to poles 3 and 4. That's one observation. We can determine the sidedness of our time domain waveform by looking at the region of convergence relationship or orientation to the pole locations. Is it clear if we had something over here let's say pole number 5, which one would it be grouped with? Would it be right-sided or left-sided? Now you can't use your hands because I'm in the left-hand plane. But if you're trying to use your hands, you could reflect 5 over into the positive half plane and do the same strategy. That's corresponding to a left-sided sequence, the pole at 5. B, if the region of convergence contains the magnitude of z equal to 1, and we have another way of referring to that. That's our unit circle. That's when z, the absolute value of z, is equal to 1. So now we have a string tied on our waistband, and we put it down at the origin, and we walk around, and that string's 1 unit length. We're going to be walking on the unit circle, right? Now you'll never forget the unit circle. It's tied to your waistband. Never mind. So now we have the unit circle. If the region of convergence contains that, then the time domain sequence does it matter if that time domain sequence is one-sided or two-sided, right-sided or left-sided? No. So this could be associated with a one-sided or a two-sided sequence. It doesn't matter. If the region of convergence contains the unit circle, what can we say about the nature of our time domain response? Is it bounded or unbounded? It's now bounded, and if it was corresponding to a system, we might say that that system is stable. In this case, it's going to depend on the values of 3 and 1, whether or not that region of convergence contains the unit circle. If pole number, how do I want to say this? Suppose pole number 3 is at 2. Can I be any more confusing? So let's let 3 be at 3. Let's say pole number 3 is at 3. Is your time domain waveform bounded? No. What if pole number 1 is at 1? Then we're at that margin, aren't we? We're right on the boundary. I don't like it. I would say no. Okay? But now what if pole number 1 was at 1.5? And I still need to tell you what 3 is, don't I? 3 could be at 1.25. Not very good, is it? What if, isn't this fun? Now we can go to a bar and draw on a napkin all of these regions of convergence, and you can find a bar in the Z-transform expansion. I have no idea. But do you see now how to interpret the region of convergence and the time interval, or the region where the little n is defined? That's what I hope you take home from tonight, and not just going to a bar or finding a bar. We will pick up at that point whenever. Monday.